Hi, let's talk about the cancellation property. The cancellation property basically says that you can cancel on each side. In other words, if you have AB equals AC, you can basically just think of canceling off the A's and you get the conclude that B equals C. So this is a nice property to have. However, it's not obvious that you're going to have it. For instance, let's just look at a quick example here with matrices. If I'm going to have something of the form AB equals AC again. And here's my A. And here's my B. It's going to be 0, 0, 1, 2. And is this equal to, my A is now this, and my C I'm going to have 0, 0, 2, 1. So now, if these two things are equal, the cancellation property would say that B and C would have to be the same. But if you do matrix multiplication on this, you'll realize that this ends up being 0, 0, 0, 0, and 0, 0, 0, 0. So if we had the cancellation property for matrices, you'd say, oh, well, I can cancel off both of these and I'd end up with those two matrices have to be equal. But they're not, because look, the row of the 2 is in a different place. So this is why the cancellation property isn't necessarily obvious. So what we're going to do is we're going to prove that you do get the cancellation property for groups, which will be nice. So we're going to start by supposing that we have equality. Just like I had the two matrices, I had the 0 matrix equal to the 0 matrix. I'm going to now prove that B has to equal C. And to do this, right, I'm going to start with AB equals AC, and I'm going to use inverses on the left on both sides by inverses. Now, I don't know that the group is going to be commutative, so I need to be very careful to put the A inverse on the left sides. I can't have, in a lot of cases, I might want to do something like 5 plus 2 equals, x plus 2. So a lot of times I might want to add -2 to both sides in high school algebra. This is very dangerous to do because here I'm adding -2 on the left and here I'm adding -2 on the right. It's fine in high school algebra because addition is commutative, but in groups you don't necessarily have commutativity. So I'm going to multiply both sides on the left, and I wouldn't write this if I were writing out a formal proof. I would just kind of assume it, but I'm writing it here for you, dear viewer, that I'm using the multiplicative property of equality. That is, when two things are equal, like this and this, that really means that they're just two different names for the same thing. And so if I do something to AB, say multiply by left by inverse, is the same thing as multiplying on the left for AC, because AB and AC are really the same thing. They're just two different names for the same thing. All right, I can move on, and I'm just going to use the associative. I would often just skip this step because groups are associative, so you don't need to worry about this. But we're going to really spell it out. Once again, I would not write this down in a formal proof, but I'm providing. Then the inverses end up giving you E, where I should really say E is the identity. Do B definitely. And keep in mind what I should have in the proof is if E is the identity of G, then if E is the identity of G, that's barely legible. Oh. So that's how the proof goes. This is a lot like high school, maybe. It's just kind of you take a formula and you just manipulate until it's what you want. But that is really the right thing to do for this proof. All right, thank you very much.